combinatorial soundness. Please take it away.
Yeah. Thank you. Can everybody hear me? Today I will tell you about quantum gap amplification. And this is a joint work with Vitali and Tina. Hopefully we'll post this very soon. Let me start by describing to you the quantum PCP conjecture, which I'm sure the audience here knows very well. So the central object of study here is a local Hamiltonian, which is a sum over local Hamiltonian terms hi, each of which has a bounded norm and acts on a bounded number of qubits. And the task of the local Hamiltonian problem is to find the ground energy density of this local Hamiltonian. Now, the story of the quantum PCP conjecture began by Kitaev's QMA theorem, where he showed that the following problem is QMA hard. The problem is deciding between the two cases. Case A, the ground energy density is approximately 0, and case B, the ground energy density is at least inverse polynomial. And the difference between these two cases is called the promise gap. The quantum PCP conjecture conjectured that this problem remains QMA hard even when the promise gap is a constant, independent of the system size. Now, to my knowledge, this was first posed by Aharonov in 2001. And the reason why this conjecture is interesting is not only because local Hamiltonians are central objects in quantum information and quantum many-body physics, but also because the classical version of this conjecture, which is the PCP theorem, is a foundational result in computer science. So we're now at 25 years after this conjecture was proposed, and we have seen some progress, especially in recent years, on some relevant questions and areas of quantum PCP, such as the resolution of the QLDPC conjecture or the NLTS conjecture. However, at least until very recently, we haven't yet seen an actual roadmap to how to prove or disprove this quantum PCP conjecture. So how should we go about approaching this problem? So of course, the most natural way is to look at the proof of the classical PCP theorem and try to learn from it. Now, classically, there are actually multiple ways to prove the PCP theorem. But in my opinion, many of these constructions rely on two main procedures. The first procedure is called gap amplification, in which we amplify the promise gap of the local Hamiltonian at the cost of blowing up the alphabet size. And then this first procedure is then compensated by the second procedure called alphabet reduction, in which we reduce the alphabet size back to the original value while not shrinking the promise gap by too much. And the key property of these two procedures is that we would like to keep the locality of the Hamiltonian unchanged. One of the most famous examples of using these two procedures to prove the PCP theorem is by Dinur, where she showed that it suffices to just iterate these two procedures again and again to prove the PCP theorem. So given the central roles of these two procedures, it is natural to ask whether or not we can quantize these two procedures in hope to prove the quantum PCP conjecture. And a lot of attention has been given to especially the first procedure, gap amplification. However, until now, it's still kind of unknown how to quantize either of these procedures. And in this work, we continue the study of gap amplification, and this is the topic of this talk. OK, so why is quantizing locality-preserving gap amplification difficult. So to see this, we can look at the most basic form of classical locality-preserving gap amplification, which is parallel repetition. So what happened in classical gap amplification is we imagine encoding the original witness into some encoding. And in parallel repetition, what happens is that this encoding maps the witness to a new proof with a larger alphabet. Each alphabet symbol is supposed to represent a subset of the original alphabet symbols in a proof. So for example, in a k-fold parallel repetition, the new proof will contain each symbol in the new proof is the value of a subset of k variables in the original proof. And on this new proof, the check remains too local. And the point is that this check is now checking many original constraints at once. And this is intuitively how we can hope to get gap amplification. And the famous Denour's proof is nothing but a de-randomization of parallel repetition, in which instead of considering all subsets of size k, she considers subsets that arise from random walks on an expander graph. More generally, classical gap amplification proceeds by encoding the witness into some locally decodable codes. So in trying to quantize these procedures, we quite obviously we will run into some conceptual quantum obstructions, which were first observed in this, which were written down in this survey by Dorit, Itai, and Tomavidic in 2013. So the first obstruction is that is the quantum no-cloning theorem. So essentially, if we look at this parallel repetition procedure, we can see that in the new proof, we're asking that the new proof has multiple copies of the original symbols of the original proof. And clearly, if we do this, if we ask to do this if the original proof is an entangled quantum state in a quantum case, then it's really unclear how we can achieve something like this in the quantum case. Now, for the furthermore, what happens in the classical gap amplification is that we're kind of under the hood encoding the witness into some locally decodable codes, and it turns out that just by construction, by definition, quantum code was locally indistinguishable. So these obstructions were further, formalized in a no-go, what viewed as a no-go theorem by Brandau and Harrow in 2013, where they showed that a quantum gap amplification procedure with parameters similar to this classical parallel repetition is impossible unless quantum PCP is false or QMA is equal to NP. So with these quantum difficulties, what did the prior works did? So there have been prior attempts in quantizing gap amplification, and because of these difficulties, all of them had to increase the locality of the Hamiltonian. Now, it turns out that locality increasing gap amplification is trivial classically by a simple procedure called serial repetition. So what happens in serial repetition is that the new proof will just be the same as the original proof. The only difference is that now, instead of just checking one constraint at once, we sample multiple random constraints together and check them and combine them together and check all of them. And this, of course, increases the locality and also increases the gap at the cost of increasing the locality. Now, it turns out that getting a quantum analogues of serial repetition is already non-trivial. and this is what achieved by the previous works. And some of the techniques, and doing this in a quantum case already required some new inherently quantum ideas, and some of these such as the detectability lemma, which has now become one of the central tools in Hamiltonian complexity. Unfortunately, it's unknown if like serial repetition type gap amplification is useful for PCP, even classically. So this brings me to our main result. In our work, we gave a candidate construction for locality-preserving quantum gap amplification. And we didn't quite manage to prove a promised gap amplification, but we instead proved a weakening statement of gap amplification. So I'll read this out now. Given a two-local input Hamiltonian, we can construct in polynomial time a two-local output Hamiltonian on a larger qudit dimension, which is 2 to the polylog, such that if the input Hamiltonian has energy 0, then H prime has energy 0. If H has energy at least epsilon, then any state must violate at least an amplified fraction of terms in H primed, which is epsilon times polylog n. Yes, Yajing?
So when you say violate the constraints, like either because it's a continuous manual, right? I mean, what's the definition of violate?
Yes, yeah, I will define it now. Thanks. So the question is, how do we define violation of a constraint? So by violation, we just mean that that constraint is violated by any non-zero amount. It could be exponentially small. And that's precisely why this statement is a weakening of the statement that we actually wanted. And the reason is because in quantum constraints, right, quantum constraint can be partially violated. So, so the actual statement we want is that for any state, the total energy is at least epsilon primed. Epsilon primed here is epsilon times polylog. What we instead get is this weakening statement where, right, this is counting how many terms do we evaluate. Yeah, Louis?
Sorry, I might be misunderstanding. But so is there like an asymmetry that the if statement is like true energy, whereas the then is like
Yes, there's an asymmetry. We can get some statement when you relax the input Hamiltonian to also have combinatorial soundness, but essentially there's some technical details that I'm hiding here that will make the output Hamiltonian not so nice in the sense that it might not be like this procedure might not be repeatable. Yeah.
Do you have any control about that non-zero number as a function?
The best we can have is at least exponentially small in a system size. Okay, so why does this notion of weakened soundness, where do we get this from? So yeah, we didn't come up with this notion out of nowhere. This is rather some known notion that has been used before. This is known as combinatorial soundness, and it was used as stepping stone in the literature of the NLTS theorem. And in more technical detail, the place where we had to weaken our statement to this combinatorial soundness statement is in our usage of a recent circuit to Hamiltonian mapping in a joint work with Anurag and Nico. I'll explain later in the talk how this comes about. Okay, any further questions? Yes, Dominic?
Non-combinatorial version violate this number?
No. We'll explain why we could. Indeed, later in the talk, I'll explain why we still can hope that the non-combinatorial version holds. And it's because the parameters of our Hamiltonian somehow avoid the regimes where Brenner-Harrow applies. Yes?
Trade off the alphabet size to how much amplification you get when you make them constants?
Yeah, so currently we cannot go, right, so the trade-off here is we pay polylog in alphabet and get polylog in the gap. We would ideally want to just trade by, we ideally want to amplify by a constant. Right now we don't know how to do that. Yeah.
Can you amplify by more than polylog?
Yes. Yeah, but in a sense, you really want to amplify it by the smallest amount possible. That's the more control you can get from here. Oh, yes, Margaret?
So actually, this left level that's in point A is approximately equal to 0 for Hamiltonian H and H prime.
They're both, say, super polynomially small.
But could be different.
Yeah, they're slightly different. They're off by some super polynomially small quantity. Okay, so before going into describing this construction, I'll just directly give you some of the key ideas in our work. So the first key idea in our work is based on a recent fault tolerance-based classical PCP by Mitali, Dorminter, and Nikhil Vyas. And using some ideas from this construction of classical PCP, we introduce a new framework to view gap amplification as fault-tolerant distributed protocol for computing violations of Hamiltonian constraints. And then we construct such a fault-tolerant protocol. And as a key ingredient in this protocol, we solved a problem of independent interest, which is we gave the first quantum multi-party computation scheme with perfect security, information theoretic security. Then we compile our distributed protocol into a local Hamiltonian using this ABN circuit to Hamiltonian. And finally, it turns out that in the analysis of our protocol, we run into some conceptual challenges in the quantum case. In particular, we run into some tension between local decodability and quantum error correction in our specific setting. So we introduce some new ideas to compromise between these two goals in our setting. Okay, so the outline of the rest of the talk, first I'll describe a template, how to view gap amplification as distributed computation. Then I'll describe our protocol, then show how to convert it to the local Hamiltonian. And I'll end by some digressions at the end. So as mentioned, our starting point is a recent fault-tolerant-based classical PCP by Mitali and co-authors. Now, of course, this paper has nothing to do with quantum, and the goal there is also very different. Like, it doesn't matter for the purpose of this talk, but I'll just mention that their goal is to get classical PCP with small soundness. Doesn't matter what this means to you, but the key thing that they need to do in their paper is they introduced a way to map from any arbitrary CSP, 2 CSP, or 2 local Hamiltonian, to a 2 CSP on some well-structured hypergraph. And they needed to do this because they wanted to do something else on this hypergraph, which you don't need to know. But okay, so the key innovation in this transformation is that they come up with a fault-tolerant routing protocol on this graph. Yes?
What does it mean to have a 2 CSP on a hypergraph?
The constraints only act on the edges of this graph.
Sorry?
You have some like hypergraph in mind, and the constraints only act on the edges of the graph. Like the bits or qubits, in their case, are like on the vertices and the
Yeah. You can forget about the hyper thing. The fact that it's a hypergraph is only used in this routing protocol. But the 2 CSP is on the edges and the vertices. Yeah. Right. So after introducing this routing protocol, they used a variant of the Cook-Levin tableau to compile their protocol into a CSP on this new graph. Their goal is only just to do this transformation without losing on the promise gap. But it turns out that what they achieved as a byproduct is a new gap amplification. So this is quite hopeful for the quantum community because this is somehow they're saying we can do gap amplification by fault tolerance, and fault tolerance is something that we know kind of know how to quantize. So so that's why we started looking at this construction. But it turns out that if you look at this construction carefully enough, what happens under the hood is based on some sort of locally copying the classical bits and doing local equality checks. Okay. So what we do instead is our first contribution is to adapt their framework and introduce a way to view gap amplification, not just as fault-tolerant routing, but as fault-tolerant computing of the constraints. So what this means is that we will imagine having a graph with players per vertex, and we'll construct a fault-tolerant distributed protocol on this graph. The input of this protocol will be some encoding of the original witness. And then upon receiving this, the players will work and communicate along the edges of this graph. And at the end, output some encoding of the constraint values of the Hamiltonian. And these values are distributed in some way so that each player at the end knows many values of the original constraints. And this protocol, if we design this protocol in a way that, say, if the original Hamiltonian if the original proof violates, say, epsilon fraction of the Hamiltonian terms, we want this final protocol, the output of this protocol is such that each player, a 2 epsilon fraction of the players will see one violation. And of course, because we're in the PCP setting, we need to construct a fault-tolerant version of this protocol. And we show how to construct such protocol by using high-dimensional expander as the underlying graph, by borrowing ideas from the BMP paper. And then we can compile the protocol into a local Hamiltonian, and then we quantize this pipeline. Yes?
What information is being passed around between the layers in this protocol?
Sorry, what is the?
What information is being passed around between the layers in this protocol?
So they can freely communicate along the edges. Like they're given the encoding of the witness in some distributed way, and they can do whatever local computation or communication they like. Okay. So here's a more detailed description of our template presented classically, which should you see that very naturally like quantizable. So first, I'll make a simplification assumption for the rest of this talk. I'll just assume that the input Hamiltonian has ground energy density inverse polylog, and the goal will be to amplify it to a constant gap. So given the input Hamiltonian, what we'll do is we first write down the circuit that computes the constraints of the Hamiltonian. So in particular, this circuit will consist of multiple layers. Each layer measures a set of non-overlapping constraints in the Hamiltonian. The input of this circuit is the proof, and the output is all the constraint values. We map this to a distributed protocol, and then we use the Cook-Levitt tableau to get a Hamiltonian out of it. Now, how do we map this circuit to a protocol? What we'll do is that we'll associate each constraint in this circuit to a local neighborhood on this graph. So for example, this constraint, the red constraint is assigned to the local neighborhood in red circle. And on this neighborhood, the players will receive the encodings of the relevant bits to this constraint, encoding of x1 and x2. Then the players within this neighborhood will communicate, do some work to jointly compute this constraint. And at the end, let's say this constraint is 1, then at the end, all the players will know the value of the constraint. Similarly, in this second constraint, let's say it's assigned to this neighborhood, they will do the same thing and compute and see all of them will know the value. Then for the next layer of the circuit, they will also do the same thing, except that these neighborhoods have to talk to each other in order to transfer the witness from one neighborhood to another. Because, for example, this yellow circle corresponds to this constraint, needs to know x2, and x2 was originally used in this red neighborhood. So this red neighborhood send the encoding of x2 to the yellow neighborhood, and then they perform the yellow neighborhood perform the constraints. So let's say this constraint is 0, then at the end, all of the players in this neighborhood has 0 values. Okay, so why do we expect gap amplification? So first, let's consider a perfect execution of this protocol. So what we know is that because the input promise gap is inverse polylog, at the end, an inverse polylog fraction of the neighborhoods will output 1s. And this in the output Hamiltonian, we'll have a term for each vertex, for each player, and each player will be penalized if they see at least 1 at the end of the protocol. So the reason we can get amplification is that it's clear from this picture. Each vertex is part of many neighborhoods. In particular, if we design the protocol so that each vertex is part of polylog many neighborhoods in some random way, then we should expect that a constant fraction of the players will see a violation at the end. Okay, and why do we need the protocol to be fault tolerant? The reason is because, well, of course, in our output Hamiltonian, we have Hamiltonian terms that check the execution of the protocol. So in particular, what happens in this Hamiltonian is that each variable of this Hamiltonian will correspond to a player in this protocol, and the assignment to that player is it's the transcript of everything that happens during the protocol. Like, and then the checks in this Hamiltonian. Oh yeah, and so the output Hamiltonian is on a qudit or an alphabet with size like proportional to the word complexity of the protocol, of each player in the protocol. And each term in the protocol Hamiltonian will check that each player performs their local computation correctly throughout the protocol, as well as checking the communication between any pair of players on the edges of the graph. So we can see that an assignment with epsilon fraction of violations on each protocol correspond directly to a protocol with epsilon fraction of corruptions on this graph. Yeah.
I'm not sure I understand. So this is a routing protocol. How should I think of this differently than a circuit? In the sense that what the same node experience many times a computation, or what's the difference exactly?
Right.
From a
Yeah.
circuit?
So the protocol you can think of as a circuit where you only allow gate in between edges that you specify. Like you don't allow arbitrary two local gates between any arbitrary pair of players. Like the gates had to follow the edges of the graph. So that's the first thing. The second thing is the second difference is in our notion of corruption. So an edge is corrupted if at any time during the protocol, like the communication is wrong. So, and same for each vertex. Like a player is corrupted if at just any time, at any point in the protocol, they perform something. They deviate from the real, the real protocol.
And this is somehow important, the fact that you're specifying an edge and not a particular gate or qubit in a circuit?
Yeah, it's like you're using this edge to group many gates, like throughout time steps, together into a single check. Yeah. Yeah, thanks for the question. So, yeah, so so for this, because of this, we need the fault-tolerant. We need the protocol to be fault-tolerant against a constant fraction of edge corruptions. So, using this property as well as the sampling property from the previous slide, we can quite easily conclude that this H-primed Hamiltonian has ground energy density at least a constant. Okay. Is that clear?
What is your notion of fault tolerates that fraction of faults?
Right. Yeah, what this means is that, okay, so in a noiseless run of the protocol, at the end, we've solved in the previous slide that a constant fraction of players will see a 1 in their local view. And here, what this fault tolerance means that that statement remains to be true even if throughout the protocol a constant fraction of edges are corrupted. Yeah, so then we can see that unless this H protocol Hamiltonian has energy above this threshold, then H out has to have energy above, has to have a constant energy. So the total energy of H prime is at least a constant. Okay, so now that you have seen the classical version of our template, then it's very natural to try to quantize this template. So again, basically, you replace everything in the previous template by like the quantum version. So first we look at the quantum sequential measurement circuit. So the input is some witness, and the output is the values of the constraints. And again, we expect an inverse polylog fraction of outcomes to be 1. Then we map it to some distributed quantum protocol. Now, what happens here is that each neighborhood will now receive a quantum encoding of the relevant qubits. And the key point is that after doing the computation, they output a classical value that says whether or not that constraint is violated. And that value is then broadcast to all the players within the associated neighborhood. And the key takeaway here is that we only broadcast the classical values at the end, rather than like copying the quantum witnesses. And this is the hope why we can circumvent no cloning in our template. And then in the final step, we can ask to perform a quantum Cook-Levin mapping to get a local Hamiltonian. Okay. Yes?
Why is there a question mark on quantum Cook-Levin?
Hmm?
Sorry, why is there a question mark on quantum Cook-Levin?
Yes, because this is, it turns out that we don't have like a circuit to Hamiltonian mapping that suffices to complete this template. And like we have some circuit to Hamiltonian that suffices to give us the combinatorial gap amplification statement in our theorem, but yeah, like we have something here, but not completely. There's still some unresolved issue with this error, which I'll describe later in later slides. Okay, so let me now describe the protocol, the high level. So what do we want for this distributed protocol? So first, as mentioned, we need to pick an underlying graph such that within each neighborhood, the players can jointly compute the constraint violation in some fault-tolerant way. And if you work in cryptography, it turns out that this task is called multi-party computation. Then we also need that the neighborhoods can communicate with each other. And for that, we need a fault-tolerant communication or routing protocol between the neighborhoods. And we need to design this graph as well as the protocol so that the work complexity per player is small throughout the protocol. In particular, this is because the work complexity goes into the alphabet size, and we want to keep it to be, say, polylog. And this in turn requires the graph to be low degree, constant or polylog, because the work complexity is at least the communication complexity, which in turn is at least the degree of the graph. Okay, so what is the underlying graph we use? Well, first we need the underlying graph to be well connected. So the natural idea that would come to your mind is obviously expanders, which are sparsifications of the complete graph. Unfortunately, it turns out that expanders don't work for us. And the reason is because the local neighborhoods of an expander are tree-like. Yes?
Sorry, can you explain again why exactly do you need where is exactly that you're using the low connectedness?
Right, yes. So at the high level, I haven't really explained why, but at the high level, well, we want to design fault-tolerant computation, like within each neighborhood and communication, fault-tolerant communication across neighborhoods, right? And we want to tolerate corruptions on the edges. So in a sense, if we want to have fault tolerance, we must have some well-connectedness in the graph, because otherwise you can corrupt the edges and disconnect the players. Right. So, yeah. So great. So that's exactly why expanders don't suffice for us, because we want each local neighborhood to be connected enough. Whereas on expanders, they are like tree-like, and trees are not fault tolerant because we can simply disconnect a tree by corrupting a few edges at the root of the tree. And this is where we turn into high-dimensional expanders. HDX are basically specifications of the complete hypergraphs. And the key advantage that we get from HDX is that their local neighborhoods are now cliques rather than a tree. And the fact that HDX could support fault tolerance was, in my understanding, first observed in this BMV paper, where they construct a fault-tolerant routing protocol on the HDX. And we use this crucially in our construction as well. OK, so the claim is that we can do fault-tolerant distributed computation on an HDX. So first, recall in the template that I showed you earlier, we need the neighborhood. We need to do computation within the neighborhood. And the neighborhood we'll use are the cliques in an HDX. And indeed, a clique supports multi-party computation, or MPC. And what this means is that given some input, the players within a clique can communicate and work with each other to jointly compute some function. In our case, the values of the constraints, even in the presence of a constant fraction of edge corruptions. So at the end, the majority of the players will still see the correct outcome of the constraint. Another property that HDX gives us is a good sampling property, meaning that if there's say a 0.01 global fraction of corrupted edges, then basically the cliques are good samplers of this fraction. Like basically for most of the cliques, you will see at most 0.01 fraction of bad edges locally, with the exception of very few cliques where the corruptions might concentrate. So what this means is that on most of the cliques, the local MPC will be computed correctly. And the final property that HDX gives us is a fault-tolerant communication protocol between cliques. And the intuition here comes from this line, because very few cliques are bad. When they communicate, like essentially most of the messages will be correct. So these three properties are why HDX could support fault tolerance, classically and also quantumly. And so we constructed a quantum distributed protocol on this HDX. In particular, on each local neighborhood, each local clique, we construct a quantum MPC protocol with zero error. essentially we construct some new quantum MPC protocol with some property that is not known before, which is zero error or perfect security. And then for the global communication between cliques, we quantize the fault-tolerant routing of the BMV paper. And combining these two ingredients, we obtain the fault-tolerant distributed protocol. Now, it turns out that the first component here, in doing this first component, we constructed a new quantum MPC scheme that solves some interesting, some problem of independent interest in the literature of multi-party computation, which I'll just mention that and not go into the details. Okay. Okay, so that's the distributed protocol. And then in the third step, we convert it to a local Hamiltonian. So as a reminder, we have a 3-step template, and we have seen how to do the first step in both classical and quantum. Now, for the second, for this second step, basically what I described to you in the template is how we do this with the classical Cook-Levin mapping. And it turns out that in the quantum case, we have some candidate to do this second step, but there's some like limitations that make us resort to combinatorial gap amplification rather than the fully general gap amplification. So how does this work? Well, at the high level, we want to map the protocol to a Hamiltonian such that the Hamiltonian can inherit the fault tolerance of the protocol. And the reason that the classical Cook-Levin works is because it has a robustness property, which I mentioned earlier. An assignment to the Cook-Levin Hamiltonian with epsilon fraction of violations is in one-to-one correspondence to a protocol with epsilon fraction of edge corruptions. Now, it turns out that in the quantum case, the Feynman-Kitaev circuit to Hamiltonian fails to have this property. And so we instead use a recent quantum mapping in a joint work with Anurag and Nico, which has some version of this property, which I'll describe in the next slide. Okay, so what is this weakened robustness property that this ABN Hamiltonian gives us? So here's a statement. So in this paper, we gave a circuit to Hamiltonian with this property. A state that violates an epsilon fraction of terms correspond to an execution of the protocol with epsilon corrupted edges. And what that means is that the state has this form. Okay, so P is the protocol, and F is the errors that happen during the protocol. And the guarantee we have is that the support of F is limited to some epsilon fraction of the edges. And the reason why this falls short of getting the robustness property in the quantum case is because of this condition. Because in general, a quantum state, an epsilon energy quantum state, doesn't have to only violate an epsilon fraction of terms in Hamiltonian. And in this construction, this paper lives as a conjecture that a similar statement to this holds for epsilon energy states.
Reverse
of terms that a Hamiltonian with epsilon violates.
Is there any bound on the number of terms?
Yeah, on the number of, yeah, on the number of terms that an epsilon energy Hamiltonian.
Pretty arbitrary, right? Like you could violate them all with like exponentially small.
Yeah.
So you have exponentially small energy, but you violate.
Yes, you can violate all of them by a little bit. So such a state is not, that's why, this statement doesn't include that kind of state. Yeah, that's why it's a weakening of a general state. Okay, so, oh yeah, Anand?
Have you said yet where the large local dimension comes from, or is that not?
I did say that, but maybe not clearly enough. So the local dimension comes from the local transcript of a player in the classical case, which equals to the work complexity of each player throughout the protocol. And in our case, that's polylog. Right. So with this weakened statement of the robustness property, we asked, can we use this statement to get a amplification for combinatorial soundness? And well, the reason is because if this conjecture holds, then we'll also need to analyze some state that look like this. So doing analysis of combinatorial soundness amplification can be viewed as a stepping stone to the general gap amplification if this conjecture holds. And so yeah, we went ahead and do this. And it turns out that analyzing the combinatorial soundness of this Hamiltonian doesn't simply reduce to just applying the fault tolerance of the protocol on this state. It turns out, and the reason that this analysis became complicated is quite surprisingly, was surprising to us, and it was quite surprising that we run into some other conceptual challenges that we didn't anticipate. So why? So the error model, the reason is the error model we consider allows a linear combination over unitary faults. In particular, we can imagine having a linear combination of the I and poly Z error. And such combination can give rise to a non-unitary errors in the protocol. And in particular, in this case, it gives rise to a post-selection error. And so, for example, we can imagine every player in the protocol runs their computation correctly up until the end, and at the end, just one corrupting player applies a post-selection error on their qubit. So why is this kind of post-selection error bad? The reason is because this single adversary can post-select on a low violation event. So as a reminder, at the end, every player within a neighborhood receives the broadcast value of the computed constraint on that neighborhood, which you can view as a repetition code encoding of the violation value. Now, at the end of an ideal execution of the protocol, we have some distribution. The output is some distribution over the violation patterns of the Hamiltonian constraints. The guarantee we have is that most of the weight will be on the high violation constraint in the soundness case. So we were hoping that that's why we were hoping that most of the players will see a lot of ones. Now the subtlety arises in the quantum case is because because of the non-commutativity of the Hamiltonian terms, we might have some non-zero weight on the very low violation event. Even like any non-zero amount of weight on this, say all constraints are satisfied. And this is bad because then a single adversary, post-selection adversary here, could collapse this entire state to this low violation part. And so our intuition earlier that we should see a lot of ones and a lot of players should see a ones would not work because of this post-selection error. So to handle this, we had to introduce a few ideas. So first, the issue seems to be that we want two conflicting goals here. So on each clique, what we did earlier was we encode the violation value into a repetition code, and each player receives 1 bit in this repetition code, right? And we do that because we want to be able to locally read out the computed value. Each player wants to see the computed value. On the other hand, because of doing that, now each player can simply, with the power of post-selection, can simply post-select on a bad outcome globally by just a local post-selection error. So to deal with this, we introduced two ideas. So the first idea is quite natural. So instead of using a repetition code output, we use a noisy repetition readout. So what we do here is that, say if the outcome is 1, so instead of just encoding, instead of repeating each bit, instead of repeating the bit, we flip the bit with a small probability. And the reason that helps us is because this is kind of like, instead of revealing the entire bit locally, we're now only revealing like 0.99 bits of information per player. And so that obscures the global information from this post-selection error by a little bit. Now, it turns out that this idea works to deal with a small number of corrupting players. But it's not enough when there are many, many players corrupting in our protocol. So to deal with that case, we introduced a second idea, which is to use honest post-selection to fight against cheating post-selection. So what we do is that after we ask the players to encode in this noisy repetition code, we ask the provers to implement this slightly non-unitary operator. And overall, the encoding of the output distribution has this form. So what this operator does is that it's deviating, it's kind of biasing the output toward 1 to fight against the post-selection adversary who are trying to bias toward 0. So this might seem unnatural to you. How can this distributed protocol implement this non-unitary operator? And so essentially what we did here is we modify the ABN Hamiltonian, and it turns out that you can modify this Hamiltonian to introduce this non-unitary operator at the end. And yeah, it turns out that these two ideas together make our analysis work, at least for combinatorial soundness. So yeah, that's the description of all steps in our construction. Now let me quickly end with some digressions. So earlier in the talk, I mentioned about the Brandel-Harrow barrier. So how do our construction get around this barrier? Well, there are at least two reasons that we can tell. The first one is kind of obvious, because we only showed that we amplified the combinatorial soundness, to which the Randall-Harrow barrier simply doesn't apply. But we do hope that our construction actually holds and actually amplifies the general non-combinatorial soundness as well, under the ABN conjecture, or maybe some future circuit to Hamiltonian mapping that satisfy the quantum robustness property. In that case, there's a second reason that explains why our construction circumvents the BH barrier. The reason is the BH barrier only forbids the regime when the output alphabet is much smaller than the degree, the degree of the output Hamiltonian. And this is not the case for our construction, because the alphabet in our case is lower bounded by the word complexity, which is in turn lower bounded by the degree of the Hamiltonian. Okay. Then this is the final slide I have. What does our construction say about the general big picture of quantum PCP? Well, it turns out that in a concurrent work by Mitali and her student, they proved the classical analog of our amplification theorem. And in combination with now standard tool of proof composition, classical proof composition, they were able to obtain a new constant soundness and constant query PCP with basically almost linear polynomial size. This suggests that the gap amplification, our gap amplification procedure might have strength comparable to what would suffice classically for a PCP theorem. However, there's still two missing ingredients. The first is quantum proof composition has not been studied yet, has not been well studied yet. And there's some folklore results around quantum proof composition. Let me just say that basically classical proof composition relies on classical PCPP, I think, and people have, I think folklore have had folklore discussion about quantum PCPP, and there's some simple no-go argument for quantum PCPP for general Hamiltonian. What we hope here is that our construction gives a specific Hamiltonian as output, so we could hope to only try to do proof composition on our output Hamiltonian. The second open question is clearly the ABN general soundness conjecture, or can we get a new circuit to Hamiltonian mapping with general soundness? And yeah, that's it for me. Thank you so much.
Thanks, Quynh, for the nice talk. Do we have questions? Oh,
yeah, Anna?
Yeah. Do you think this perspective from like routing protocols will help for alphabet reduction? Like, can you do classical alphabet reduction with this, or do you use other tools?
I think the perspective of fault tolerance will be useful, and maybe not just routing. Yeah. Yes.
You said that there's some simple no-go argument against quantum PCP.
Yeah.
Is there like?
Yeah, it's very obvious. Like essentially, PCPP asks that you can verify proximity to a classical code word by just doing local check, and clearly that doesn't do. You can't do that for quantum code because of local indistinguishability. Yeah. Yes, Louis.
So like in this.
No, you can go.
In this thing you mentioned at the end, like, is there any additional like starting thing or exponential size PCP, or is it really just like you start from like NP and then you just
You do need some weaker PCP for classical proof composition, like maybe Hadamard PCPP or some other details that maybe Vitaly can tell you. But for sure, in any construction, you need some like weaker PCPP to do proof composition, I think.
So Hadamard doesn't suffice, like in the news proof. Hadamard, like you could increase the gap and compose with Hadamard. Because the alphabet size she blows up by is a constant, but here you blow up by polylog, so Hadamard will not suffice. So you need like this new PCP by Madhu and his students, which has like sub-exponential length, so it's better than Hadamard.
So it's still a lot longer than like polynomial, but
You can compose with like 2 to the n to the epsilon PCP, because you can just polylog will be 2 to the polylog to the 1/4 will be enough.
Nice.
This like perspective of the distributed computation thing that pops up in the gap amplification, is it also kind of in like the Diner gap amplification if you like stare at it in the right way, or is it just completely different?
Yeah, you can try very hard and frame Diner in that in some kind of distributed computation. But in the proof, in the proof of the gap amplified Hamiltonian in Diner, essentially you just do that new proof is still just some repetitions of the original proof. So there's no computation done there. All the computation is still uploaded to the local checks in Diner construction, and that makes use of some properties of. You can view as the Diner construction as making use of the like transversal gates, universal transversal gates, and like local decodability of repetition code. That's my view. Maybe Tina and Vitaly can say a bit more.
I think the case is like you can view that as a distributed, like you can view most PCPs as like a distributed computation, and you just like say, okay, every variable is a player, and like the checks correspond to combinatorial.
Yeah.
But the central idea here is not necessarily like the central idea is that all the classical ones kind of rely on like distributing the information about the witness itself between the players, and here we're like encoding it and secret sharing it. I think that's the main difference that allows us to get the quantum version. And this doesn't work on Diner because the local label participants set are not researchers, and this doesn't support like secret shared computation.
Nice. Yeah.
Yeah, like it's actually open. I mean, we tried a little bit, but it's open to. Like we don't know if we could just amplify by a constant or use expandographs instead of HDX. Because if we were able to use expandographs, maybe we can amplify just by a constant.
Yeah.
That might be helpful.
Any other questions?
Any more questions? If not, let's thank Quynh again. Yeah, that's it for today. Thank you very much.